In this second video, dealing with special topics related to the properties of gases, I'd like to talk about the stoichiometry of gas phase reactions. Now, you know that every stoichiometry problem begins with a balanced chemical equation. For example, 2 moles of hydrogen reacts with 1 mole of oxygen to form 2 moles of water. In Chapter 9, here are the types of questions we asked. Given a certain mass of hydrogen gas, one reactant, what mass of oxygen gas, the other reactant, do we need to completely use it up? And what mass of water, the product, will be formed? However, if the components aren't solids or liquids but are in the gas phase, we're not dealing with masses because we can't easily measure the masses of hydrogen, oxygen, or water vapor. Instead, we measure the volumes, so we can ask the questions, given a certain volume of hydrogen gas, what volume of oxygen gas do we need, and what volume of water vapor will be formed at constant temperature and pressure. A different type of question, but we use the same concepts. So let's look and see how we can approach this. Here is an example of a volume-to-volume stoichiometry problem, where we are given the volume of one component and we're asked to calculate the corresponding volume of another component. We begin with the chemical reaction. Nitrogen and hydrogen gas react to form ammonia gas at constant temperature and pressure. Obviously, we have to begin by writing and balancing an equation. Nitrogen gas and hydrogen gas are both diatomic molecules, and ammonia has the formula NH3. These are all in the gas phase, and I'll balance them by putting a coefficient of 2 there and a coefficient of 3 here. My first question is, what volume of nitrogen gas do I need to react completely with 5.69 liters of hydrogen gas at constant temperature and pressure? Now, we have from our balanced equation the mole ratios. For every 1 mole of nitrogen, we need 3 moles of hydrogen, and we expect to get 2 moles of ammonia. We learned that the coefficients of the balanced equation tell us the relative number of moles of reactants and products. But here, we're given volume, not moles. But what we learned earlier in this unit is that at constant temperature and pressure, moles and volume are directly proportional. And in fact, we learned that at constant temperature and pressure, the mole ratios can simply be replaced by volume ratios. So we're going to solve the stoichiometry problem by using volume ratios instead of mole ratios. And here is how it looks like. We'll begin by writing down the quantity that we're given, 5.69 liters of hydrogen gas, over 1 if you like, and we will multiply that by a volume ratio that tells us how many liters of nitrogen are needed for every liter of hydrogen. Well, just as we took numbers in mole ratios directly from the stoichiometric coefficients in the balanced equation, in the same way we will take our volume ratios, the numbers in the volume ratios, directly from the stoichiometric coefficients. So the balanced equation tells us I need 1 liter of nitrogen gas for every 3 liters of hydrogen gas to give me a volume of 1.90 liters of nitrogen gas required. The easiest kind of stoichiometry problem in the world, simply replace a mole ratio with a volume ratio. And my next question, what volume of ammonia gas will be produced in this reaction? Well, I can do exactly the same process. Begin by writing down what I'm given, 5.69 liters of hydrogen gas over 1. And now I need a volume ratio that tells me how many liters of ammonia gas will be produced per each liter of hydrogen gas. Once again, the numbers in the volume ratio come directly from the coefficients of the balanced equation. They tell me I will get 2 liters of ammonia gas for every 3 liters of hydrogen gas for a final value of 3.80 liters of ammonia. And that makes sense because that's twice the volume of nitrogen gas we needed, consistent with the fact that the coefficient before ammonia is twice that of N2. Now, what about a mass to volume stoichiometry problem? Okay, this is a little bit more complicated. Aluminum metal reacts with chlorine gas. Let's write the equation. Aluminum is a solid, chlorine is a gas. We know from way back in chapter 8 that we can predict the formula as AlCl3, a solid, and that we can balance this by using coefficients of 2 and 3 to balance chlorine and 2 to balance the aluminum. Here's our question. What volume of chlorine gas measured at a certain temperature and pressure is needed to react completely with a given mass of aluminum metal to form aluminum chloride? Well, let's do a little roadmap to sort of keep in mind what we're trying to do. We're starting with a mass of aluminum. The only thing we can convert grams of aluminum to is moles of aluminum, and we do that by dividing by the molar mass. Because we are trying to find the amount of chlorine we need to react with that amount of aluminum, we know in the second step, in which we convert from moles of aluminum to moles of chlorine, we're going to have to multiply by a mole ratio. We cannot use a volume ratio because aluminum is not a gas, it's a solid, so we have to use a mole ratio. Finally, in the last step, because the question asks not for moles of chlorine needed, but volume of chlorine gas at a given temperature and pressure, we're going to have to convert from moles of chlorine to volume of chlorine. Well, how do we do that? How do we go from moles of a gas at a specified temperature and pressure to volume of the gas? Why, the ideal gas law, of course. We'll simply use the rearranged ideal gas law, volume equals nRT over P. So, let's begin by calculating our moles of chlorine, which of course is N in the ideal gas law. So we'll start by taking our 10.4 grams of aluminum, divide by the molar mass of aluminum, 26.98 grams per mole. There's step 1. In step 2, I'll multiply that by the mole ratio, 3 moles of chlorine needed for every 2 moles of aluminum I react with, and that gives me 0.578206 moles of chlorine. Clearly I'm writing all those numbers down because I'm not finished yet, so I'm not rounding. I'm keeping lots of sig figs. And then, in the third step, to convert from moles of chlorine to volume, I'm going to use the rearranged ideal gas law, volume equals nRT over P. I'll plug in the moles of chlorine I just calculated, 0.578206 moles, times the gas constant R, with units of liter atmospheres per mole Kelvin, times the temperature. Oh, temperature was in degrees Celsius. What do I have to do? I'm just going to take 38 degrees Celsius and add 273 to that to give me temperature in Kelvin. Divide that by the pressure of 1.63 atmospheres, and that tells me that I need a volume of 9.05 liters of chlorine gas at the specified temperature and pressure to react with 10.4 grams of aluminum. So, to summarize, there are 2 types of stoichiometry problems that involve gases. The first we saw is a volume-to-volume calculation. Both the components must be in the gas phase, and the quantities that we're comparing are volumes of the gaseous components in any volume unit, measured at constant temperature and pressure. The method we use is simply to replace the mole ratio with a volume ratio. The volume ratio has the same numerical values. It has the same numbers in the numerator and denominator as a mole ratio. The only difference is that it has units of volume instead of units of moles. The second type of problem is a mass to volume calculation. One component is in the gas phase, the other is in the solid phase. The volume of the gas is expressed in liters. The mass of the solid component is expressed in grams. All we have to do is remember that to interconvert between the mass of the solid and the moles of the solid, we have to use the molar mass. So to go from grams to moles, we divide by the molar mass. To go from moles to grams, we multiply by the molar mass. But to convert between the volume of the gas and moles of the gas, we have to use the ideal gas law. To go from volume to moles, we use moles equals PV over RT. To go from moles to volume, we use volume equals nRT over P. And obviously, in this case, we need the pressure and temperature in order to perform that calculation. Let's do one more example that incorporates both types. Iron 3 sulfide reacts with oxygen to form metallic iron and gaseous sulfur trioxide. What volume of oxygen gas measured at a certain temperature and pressure do we need in order to completely react with a certain mass of iron 3 sulfide? Very similar to the previous problem. We'll begin by writing the equation. Iron 3 sulfide has the formula Fe2S3. Oxygen is a diatomic pure element. Iron metal is a solid, and sulfur trioxide gas has the formula SO3. To balance the equation, I need coefficients of 2, 9, 4, and 6. Question number 1, what volume of oxygen do we need measured at this particular temperature and pressure? Already read this, so I don't need to go through it. Let's do a little roadmap. Again, beginning with the mass of iron, we can only convert that into moles of iron. Mass of iron 3 sulfide, which is our starting reactant that we're given, must be converted to moles of iron 3 sulfide, which we must convert to moles of oxygen needed, which we will convert to volume of oxygen needed. I'm going to set this up as a single mathematical operation because I can, and in the ideal gas law will be moles of oxygen required, which will come from moles of iron 3 sulfide we begin with. So writing the equation, volume equals nRT over P. I begin with my 10.0 grams of iron 3 sulfide. I'll convert that to moles by dividing by its molar mass, 207.91 grams per mole. And I'll convert moles of iron 3 sulfide I'm starting with to moles of O2 I need by multiplying by the mole ratio, 9 moles of O2 needed for every 2 moles of iron 3 sulfide. Okay, so what I've drawn so far is N in the ideal gas law, that is moles of O2 needed. So I'll multiply that by R, 0.08206 liter atmospheres per mole Kelvin, times temperature. Oh, look, what did I forget to do? I forgot to convert from Celsius to Kelvin, so let's do that. 65 degrees Celsius plus 273 gives me a temperature of 338 Kelvin. All of that divided by the pressure at which I measure the O2, which is 1.25 atmospheres. Hey, let's do some unit conversion just for fun. Grams of iron 3 sulfide cancel grams of iron 3 sulfide. Moles of iron 3 sulfide cancel moles of iron 3 sulfide. Moles of oxygen cancel moles of oxygen. Kelvin cancels Kelvin. Atmospheres in the numerator of R cancels atmospheres in the denominator. That leaves me with units of liters, which is what I expect for volume. And that gives me, for this problem, a volume of 4.80 liters of oxygen required. Very similar to the previous problem. Now the final question, what volume of sulfur trioxide measured at the same temperature and pressure will be produced? Sulfur trioxide is a product. So starting with a certain mass of a solid reactant, I calculated the volume of gaseous co-reactant I need, and now I'm calculating the volume of gaseous product that was formed. Now, you might think that the way to do this is similar to how we solved part A, which would be to go from the mass of iron 3 sulfide to moles of iron 3 sulfide to moles of sulfur dioxide produced to volume of sulfur trioxide produced. And if you did it that way, like we did in the previous problem, you would be correct. You would get the right answer. But notice that we already know how many liters of oxygen gas we're reacting at a certain temperature and pressure. We're trying to calculate how many liters of sulfur trioxide gas will be produced at the same temperature and pressure. This becomes a gas-to-gas stoichiometry problem. So make your life easier by simply using a volume ratio instead of a mole ratio. We can do that because they are both gases being measured at the same pressure and temperature. So I will simply take just to make this very clear, what we're going to do is simply go from the volume of O2 to directly to the volume of sulfur trioxide. So I will take the 4.80 liters of O2 that we calculated in the first step, multiply that by a volume ratio. That gives me liters of sulfur trioxide produced per liter of O2 reacted. Just like in a mole ratio, the numbers in a volume ratio come directly from the stoichiometric coefficients in the balanced equation, and the balanced equation tells me that I will get 6 liters of sulfur trioxide gas for every 9 liters of O2. I'll plug those in, and that gives me 3.20 liters of sulfur trioxide gas expected. So here is a problem, a two-part problem that includes both a mass to volume stoichiometry calculation and a volume to volume stoichiometry calculation. And that's it for this unit.